All right, moving on to page 3 of the review. Number 12, a student divided f of x equals x cubed plus 8x squared minus 9x minus 3 by x minus 2 and got a remainder of 19. Explain how the student could verify if the remainder was correct. So if you want to check to see if the remainder is 19, you can use the remainder theorem. The remainder theorem says to plug in, this is x minus 2, so tricky x, if you plug in a positive 2 to your function. So plug in a 2, f of 2, for all the x's, so 2 to the third power plus 8, not x, 8 times 2 squared minus 9x geez, I keep doing that, minus 9 times 2 minus 3 to see if you get a remainder of 19. So if you are very careful with your parentheses and type this in just like that, we see that we do get a remainder of 19. So check, we know that we have verified that that remainder is correct. We use the remainder theorem. So again, if you want to take a polynomial and divide it by something like this, an x minus 2, plug in the tricky x for your x's, and what you get back will be the remainder. All right, so number 13, is g of x a factor of this polynomial? Explain your reasoning. So you could do this a couple ways. You could do the division and see if it divided evenly. Because we want to know if x plus 3 is a factor, that means that we would get a 0 remainder. We also could do the remainder theorem to see what the remainder is. So whatever really you feel like doing, with the remainder theorem, you would just plug in a -3. So what's g of -3? You have to use parentheses, otherwise we're going to get a wrong answer. But if you use parentheses when you plug this in, and then do all that math on your calculator, and you get a 0 back. That means that 0 is the remainder. So x plus 3, is it a factor? Sure is. It divided evenly because you did not get a remainder. Again, another thing you could have done is you could have shown that with synthetic division and shown that the remainder was 0 when you divided it. All right, number 14. The area of a rectangle is 4x cubed plus 14x squared minus 18 inches squared. The length of the rectangle is x plus 3. What is the width of the rectangle? So we know that area is equal to length times width. So if we take the area that we are given and divide it by the length, the result will be the width. So we are going to do division here. We're dividing by an x plus 3, so we can do synthetic. So in the corner, we're going to do our tricky x -3. We're going to fill in our coefficients, see if we're missing anything. We have our x cubed, x squared. We're missing the x to the first power, so we're going to have a 0 between the 14 and the -18. All right, so 4 is our coefficient of x cubed, 14 is the coefficient of x squared, 0 is the coefficient of x, and -18 is our constant. All right, so synthetic division, carry down the 4. Now we multiply to the corner. We get -12. Add down gives us 2. 2 times -3 is -6. Add down, we get -6. Multiply the corner, we get a +18. Add down, and we get a 0 remainder. So it divided evenly. So this is our answer. We just have to fill in the x's. Remember, we've got constant term of -6. X to the first power goes with the 2, and x to the second power goes with the 4. So the length is x plus 3. The width is 4x squared plus 2x minus 6. All right, let's take a look at some graphs. Here I'm going to zoom in a little on this. Well, there we go. Let's take a look at this graph. All right, so directions say to, I guess, sketch the graph of the function. So let's find the zeros of the function. Let's talk about the end behavior. Let's throw in a y-intercept. That'll help us. And then we can answer the questions below. Let's answer the questions below first, actually. This is in standard form. So the leading coefficient is the coefficient of the leading term. Our leading coefficient is 2. Number of terms, we have 1, 2, 3, 4, 5 terms. And the degree of the polynomial is the highest exponent, which is the 4th power. So the degree of the polynomial is 4. All right, so you can identify the zeros of your function by, I would say we could factor this and find the zeros that way. In this example, we have 1, 2, 3. It's a 5-term polynomial. So let's just type that into our graphing calculator. We can see the zeros from the graph. Let's list those off over here. The zeros of our function, we can see that they happen at -4, -1, 3, and 2.5. So definitely have your graphing calculator out and verify. Make sure that you're understanding where these numbers are coming from. We can plot those on our graph at -4. Remember, your zeros are your x-intercepts. -1, 3, and 2.5. Those are kind of close to each other. All right, we have a y-intercept. Y-intercept, plug in a 0 for all these x's. You're left with that term on the end. Your constant term will always be your y-intercept. So let's see, 1, 2, 3, 4, 5, 6. I will just count by tens. So there's the y-intercept of 60 up there. I'll make sure I go through that. And then end behavior. Let's get the end behavior of our graph going. So end behavior. As x approaches positive infinity, so that's the right side of your graph, what is your graph doing? The leading coefficient tells you what's happening on the right side. Leading coefficient is a +2, so our graph is going to go up on the right. So y is approaching positive infinity. All right, the left side of your graph over here, negative infinity, as x approaches negative infinity. Now the left side of your graph is determined by the degree. The degree is 4. If you have an even degree, your polynomial is going to have the same end behavior as the right side. So we're going to go up on the left. So your y's will approach positive infinity. Okay. So now that we know the end behaviors are and we've got the zeros of the function, we can go ahead and do a sketch of our graph. We're going to be heading this direction. We're going to catch that intercept. We're going to come through and catch this intercept. We're going to go up to our y-intercept. We're going to come down to our next x-intercept, get that intercept, and head off for our end behavior going up on both sides. There you go. All right, let's try another one of those. Okay, so this one, I want to find the zeros by factoring. I want to make sure we have the skills to do this without just typing it into a graphing calculator. So if we factor this, we can factor an x out of all 3 terms, leaves us with x squared minus x minus 20. So that's a nice little trinomial. Are there factors of -20 that add up to -1? Those factors would be a -5 and a +4. Now that we see factored form, we're going to set each factor equal to 0. So the zeros of our function will be at a 0, a +5, and a -4. So let's go ahead and plot those. We've got 0, 1, 2, 3, 4, +5, 1, 2, 3, 4, -4. All right, leading coefficient comes from our leading term right here. The coefficient of that term is 1. Number of terms, we can see that there are 3 of them, and the degree of the polynomial is 3. We also can get our y-intercept. I feel like I'm jumping all over the place here. Y-intercept is if you plug in a 0 for your x's. See how we're missing the constant term on this one? If you plug in a 0 for your x's, you just have a 0. And we already have an intercept right there. So this is a spot where the x-intercept and the y-intercept are the same point. So the y-intercept is at 0, but it's already plotted. Now let's get our end behavior. So this is always a good review to talk about end behavior. As x approaches infinity on the right side of your graph, the leading coefficient tells us what's happening. Our leading coefficient is a positive 1, so your y's will approach a positive infinity. So that means your graph is going up on the right. As x approaches a negative infinity, that's over here on the left side, negative infinity, your y's will approach the degree is the thing that tells you what's happening over here. This polynomial has a degree of 3. It's an odd number. Odd degrees will have opposite end behaviors as the right side. On the right side, we're going up, so on the left side, we've got to go down. So your y's will approach a negative infinity. Okay, let's sketch this in. We can see the end behaviors and our zeros that we're going to hit. We're going to go up through here, hit the other one, and that's a pretty decent sketch of the polynomial.